Good morning. Today we can say the last case for the damping system vibration analysis. We can saw in the last two video the critical damping system and the underdamped system. Today we can see the overdamped system for the single degree of freedom system SDOF. You can see here the system used. There is the mass M, where is applied and force PT, and there are also the force of spring Fs and force Fd of damp and the inertial force Fe. So we can, for the equilibrium of system using the second law of motion, we can write Fe plus Ft plus Fs is equal to Pt, where Fe is the inertial force equal of mass for the acceleration, Fd is the damping force equal of coefficient, damping coefficient for the velocity. Fs is the spring force for spring force equal of k stiffness of spring for the displacement. So the first equation we can write in this way: mass for acceleration plus c damping coefficient for the velocity plus k for the displacement x equal of pt. For free vibration, pt, the force applied, is equal to 0. So the second equation we can rewrite as m for acceleration plus c for velocity plus k for displacement is equal to 0. The solution of this differential equation is equal of x equal displacement x in function of time equal of g coefficient for exponential of s coefficient for the time t. In the last video we can show the critical damping system, and this is the graph of the displacement, and the underdamping system with this graph. Now we can say the overdamping system. The overdamped system, the condition is the rapport Xi of coefficient of damped coefficient C divide for critical damped coefficient must be bigger of 1. So the equation 6, remember the equation 6, this equation 6 we can write in this rewrite in this case in this way. So S is equal to Xi for omega plus when omega for rising of Xi elevated 2 minus 1. So we can compact this equation in this way, where the symbol omega cover is equal omega for rising of Xi elevated 2 when 1. The solution of the displacement in function g1, g2, and is right in function of exponential in this way. Remember where the exponential of x is equal sine hyperbolic of x plus cosine hyperbolic of x. So this equation we can rewrite in function of sine and cosine hyperbolic. Differential the displacement, this equation of displacement in function of the time, we obtain the velocity term. So the velocity is equal of this this solution, this equation. The motion is overdamped system is not oscillatory, that is not cross the mean position. It's similar to the motion of critical damped system and return towards of the mean position. Is low to damp ratio. And we can see the solution in this figure 1. So we can see the zero, the curve not touch the point 0, the axis correspondent of point 0 of the placement. And similar of critical graph of critical damped system, where the critical damped system converge to 0 faster respect of this solution. Okay, now we can implement the equation and the solution with Python code, So, okay, we can see line by line. In the 38 line, there is the library. Go to import the library. NumPy is the library which provide powerful math function and tools for working with array. Matplotlib is the library which you will use to draw the chart. And scipy is a numerical solver for ordinary differential equation ODE. Define in the line 41, they define the equation, the differential equation. There is the mass put equal 1 in kilogram. K is the stiffness in 100 in Newton for meter. C, the coefficient, damping coefficient, Newton second for meter. So we can calculate C equal of this formula, and omega, the natural frequency of a system in radiant for second. In the line 54 and 56, xv is equal to z0 and z1 represent the current displacement of time 0 and the velocity the time 0 and the velocity. dx dt is equal of velocity, and dv dt represent the acceleration, and return the displacement and the velocity, and this function return the velocity and the acceleration. After define three conditions, case 1, 2, and 3, where define the initial condition of displacement. x0 of time 0 is in the first case is equal to 0, and the velocity is equal to 0.1 meter per second. And okay, and after plot in function of time with in the range 0 3.5 second with the step 0.0.5. And okay, here in the line 76 there is the loop to solve the three case. and solve the ordinary differential equation called the function odeint and define in this equation. So calculate the minimum and maximum value of displacement and the velocity and the print, and after the plot the graph of displacement and the velocity, and save all this graph in file Overdamped System in PDF. This is the output of this output of Python code. We can see in the first graph the displacement function of time, and after in the second the velocity function of time. In the three case 1, 2, and 3 were define the initial condition. We can see now the simulation of this case, or this case. This is the first case, function of time. Here there is the system show. This is the second case, and this is the third case. Here there is the table where is write the value mass, stiffness, and damping ratio, and the critical damping calculate. And here the initial condition of the displacement and velocity. And so is the second, and this is the third. Okay. Thank you. Bye.